Hey guys, I'm Mukund D'Souza and welcome back to my YouTube channel Mucomatrix. So continuing from the previous video, a complete bipartite graph. The complete bipartite graph of m and n vertices denoted by km, n is a bipartite graph whose vertex set is partitioned into set V1 with m vertices and V2 with n vertices, in which there is an edge between each pair of vertices V1 and V2, where V1 belongs to V1 and V2 belongs to capital V2. So basically it's a bipartite graph which is complete. So these are examples, km, n. So m vertices and n vertices. Here k1, 1 vertex each. k1, 2, 1 and 2 vertices. 2, 3, 2 vertices and 3 vertices in the two partitions. So just like a bipartite graph, these are the two partitions, and being complete there must be an edge between each vertex of each partition. So in this case there's an edge between the two partitions, and edges between the two partitions, but no edge within the partition. An observation: km, n has m plus n vertices and m n edges. M plus n vertices because there are m vertices and n vertices, so the total number of vertices are m plus n. M n edges because each vertex, if we consider this as one partition and the second partition, if we consider the m vertices here and n vertices in the second, each vertex is connected to n vertices. And there are m of these, so m into n of these. Even if we go vice versa, n vertices connect to m, so m but n times because there are n vertices. Prove that a graph which contains a triangle cannot be bipartite. Now when we consider a triangle, at least two of the three vertices of a triangle must lie in one of the bipartite sets. This is because no matter how we rotate the triangle, there will always be at least two vertices in one partition. Since the two vertices are joined by an edge, as it is a triangle, the graph cannot be bipartite, as within a partition there must not be any edge. Prove that the number of edges in a bipartite graph with n vertices is at most n square by 4. Let G be a bipartite graph with n vertices. Let V1, V2 be the bipartition of G. Let V1 contain x vertices and V2 contain n minus x vertices. This is because the total is n, so x plus n minus x gives the total n vertices. G will contain maximum number of edges if every vertex in V1 is connected to V2. That is, if G is a complete bipartite. In a complete bipartite, there is an edge between every partition, between each partition, both the partitions, So therefore, the complete bipartite graph will be k, x, n minus x, as there are x vertices and n minus x vertices in the two partitions. Hence, the maximum number of edges is x into n minus x, as we have mentioned that km, n has m n edges. Now since we want to know that the maximum number of edges, at most means maximum, so we use maximization. So we assume this to be a function f of x equal to x into n minus x, which is the same as nx minus x squared. For maximization, we take the derivative and we find the double derivative. The derivative of nx minus x square is n, into the derivative of x is 1, minus the derivative of x square is 2x. Double derivative of this, n is a constant, it's 0, and derivative of minus 2x is minus 2, the coefficient of x. Since the double derivative is a negative number, that is it's less than 0, it has a maxima. The maxima being when we equate the derivative to 0. F has maximum point given by f dash of x equal to 0. F dash of x is nothing but n minus 2x. So n minus 2x equal to 0, which implies that x equal to n by 2. Therefore f has maximum value at x equal to n by 2. So basically what this means is, if we have n vertices, we split the two vertices exactly into half. So half the vertices in the top set in one partition and half the vertices in the second partition. So this is an example. These are examples. Total are two vertices, partition being 1 and 1. So the total number, the maximum number of edges is 2, because the total vertices are 2. 2 square by 4, which is nothing but 4 by 4, which is 1. And here 4 vertices, 2 in each partition. So 4 square, as the total vertices are 4. 4 square by 4, which is nothing but 1 4 cancels. Therefore it's 4. As you can see, 1 2 3 4. If we have odd number of vertices, as in this example, we cannot, even though we apply the formula n square by 4, it means at most. So if we consider this 3 square by 4, which is nothing but 9 by 4, but it's a fraction. But what this means is it can be at most 9 by 4. It need not be exactly 9 by 4. Therefore, the maximum number of edges is x into n minus x, x being n by 2, so n by 2 into n minus n by 2. This is nothing but n by 2, so n by 2 into n by 2, which is n square by 4. Hence the theorem is verified. Complement of a graph. The complement g prime of g is defined as a simple graph with same vertex set as g, and the two vertices are adjacent only when they are not adjacent in G, or vice versa. So we have the main graph G. We notice that in the complement, whatever edges are present, or in other words where the vertices are adjacent, they are not adjacent in the complement. For example, these two vertices, these two, these two, these two, these two, and these two, and vice versa. So basically whatever is not adjacent is adjacent here. So a comma f, a and f are adjacent, these are adjacent, as in all these vertices. Hence is the complement of G, and vice versa.